Hey, good morning everybody. This is Mr. Ainsworth, and we're going to get into volume review 3. And take a look at this problem here. We're going to consider the base of a solid is bounded by y equals x cubed now. Y equals 0, which is the x-axis. Okay, and x equals 1, which is the vertical line. And we're going to bound that region. It's going to be the base of the solid now, and we're going to find the volume of the solid for each of the following cross sections when taken perpendicular to the y-axis, and I'll talk about that after I draw my bounded region. We're going to do it by squares, then by semicircles, and then equilateral triangles, and then lastly we're going to do rectangles with height 2. Alright, we're going to graph the bounded region first. The first thing I do is I'm going to take a look at, I'm going to scale the axis here. I'm going to set that equal to 1, this equal to 1, just kind of so I can expand a little bit better here. I want to graph y equals x cubed, and I know that when x is 0, y is 0. In fact, you know what? I'll make it real simple here. I'll just do a table of values real quickly. Okay, so when we're only considering this between, well, it's going to be between 0 and 1 when we're finished, but you probably don't know that, so I'll just do this here. Negative 1 cubed is negative 1, 0, 0 cubed is 0, 1. Let's do a half here. A half here, half cubed is 1/8. All right, and then 1. Sorry about that. 1/2 cubed is 1/8, and then 1 cubed is 1. So if I graph those points, I get 0, 0. Here is a half. 1/8 is, let me see, this is a half here. This is a fourth. Okay, 1/8 is here. So a half comma 1/8 is right here, and then 1 comma 1 is way up here. So when you graph this cubic here, it looks like this. And then of course it comes way down here. So this is y equals x cubed. We're going to bound that between y equals 0, that's the x-axis. Okay, there you go, and x equals 1 here. Okay, so let's bound that region. Let's shade it in. Should be a little bit more narrow than that, but that's close enough for government work. Okay, so there's a bounded region there. We've got x equals 1 here. We've got y equals 0 here, the x-axis. Okay, and then we've got x cubed here. So you bound the region, and then you form your cross sections. Now we want cross sections taken to perpendicular to the y-axis. In our lesson, we did perpendicular to the x-axis, so we made them vertical here. All right, that's parallel to the y-axis. We want them perpendicular to the x-axis, so our cross section is going to be here. Okay, or you can make it here. You can make it anywhere you want. All right, and from that we're going to build squares and then semicircles. Like here's a square in 3 dimensions. Here's a semicircle. No. Okay, or triangles. You know, whatever you want. Rectangles, height 2. Right here. All right, there's height 2. We're going to take these cross sections and we're going to build these solids with known cross sections and work through them. So the first thing we do is we figure out the base of the solid. Now the base of the solid is right here, this cross section. We need that distance. All right, what is that distance? Oh, and by the way, before I do all that work here, let me just show you that when you rotate these axes like we do in class, to draw them a little bit better in 3 dimensions, all you have to do is rotate them. Now this becomes the y-axis, the x-axis here. Let's say this is 1 here, this is 0, 1's way up here. So we got this vertical line here. The function goes no, right about there. And so this region here that I just rotated looks this way when you rotate it. So when you do your cross sections, you can see them a little bit better. Here's a square built. Here's a semicircle built. So what you're doing is you're building squares and semicircles and then little rectangles, height 2, let's say. Okay? And you're going to do that one thing at a time. So the first thing we need to do is get the base of your cross section. Okay, let's base of the cross section, because that forms the side of the square. That forms a diameter here. This is the diameter. Okay, this becomes the side of the square, side of square, and what? Oops, side of side, not side of side, but how about side of square here? Once you understand this, then it just becomes a geometric problem. All you have to do is know the geometric formulas to find these areas, and then it becomes easy. Okay, but you got to get your base of the cross section first. All right, which is the side of the square, or the diameter, or so on. What does that equal to? Well, this distance here is horizontal, and we got to figure out that distance. And that distance we'll call its base of cross section here is equal to the right minus left. Okay, because it's horizontal, as you guys know. So right minus left, and we figure that distance there from taking the right side minus the left side. The right side's at 1, and the left side's given by, this x value here. But what is that x value? Well, we got to solve for that. So if I take this cube root of both sides here, you notice that the cube root of y equals x. So I'll put down the cube root of y here. So the distance between these 2 points here is 1 minus the cube root of y. That distance, 1 minus, let me write that a little bit better, the cube root of y. It's the difference between two x values. But like I said, what is that x value on the function right here? Well, you got to solve for x in the function, and you get the cube root of y. So your base of the cross section is 1 minus the cube root of y. That will form the side of the square, or the diameter of the semicircle, or the side of the equilateral triangle, or the side of the rectangle with height 2. Okay, you're going to use that in all of them. Okay, so let's get started with squares. Okay, so squares, the side is going to become 1 minus the cube root of y. And the very first thing we do in all these problems is figure out a of x. Alright, so my cross-sectional area for a square is simply side squared. So I take 1 minus the cube root of y, and I square it. And I want to simplify this before I integrate. Okay? And so what do I get? I get 1 minus 2 times, and again, y to the cube root of y, by the way, is y to the 1/3 power. So keep that in mind. You multiply these two, so you get negative cube root of y, double it, you get negative 2 times the cube root of y, and then you want to square the last. When you square y to the 1/3 power, you get y to the 2/3 power. You get this right here for the area. This is your a of x, the cross-sectional area. Now what you want to do is you want to find the volume. The volume is found by integrating from, in this case, 0 to 1. The bounds are seen vertically. Since our cross sections are horizontal, the first cross section here is at 0, and then all the way up here to 1. All right, so from 0 all the way to 1. So your bounds are found vertically. 0 to 1, a equals 0, b equals 1. And that's going to be true for all your integrals. So I'm going to say that my integral is from 0 to 1 of my cross-sectional area, which is 1 minus 2 times the cube root of y plus y to the 2/3 power, dy in this case. Okay, your thickness here is dy right here, and there's your thickness dy. Okay, all right, and then you just integrate this. You can use your calculator, of course, and I suggest you do so. And first integrate, though, we'll do one step at least. So integral 1 is y minus 2 times the integral of y to the 1/3 power. So you're going to add 1. That's 4/3. So you're going to have y to the 4/3 power here, divided by 4/3, or multiplied by 3/4. As you can tell, that's 6/4 here, and that's going to become 3/2 in here in a minute when I simplify it. Plus y to the 2/3 plus 1, or 5/3, divided by 5/3, which is multiplied by 3/5, evaluated at 0 to 1, or from 0 to 1. What do we get? We get 1 minus, again, this is 3/2 here. You can see it right here. There's 3/2. So 1 minus 3/2 times 1, all right, plus 3/5, and the whole thing evaluated at 0 is 0. So 1 minus 1/2 plus 3/5 is negative 1/2 plus 3/5. Let me see. So let's go to tenths here, and that's going to be equal to, let's see, negative 5/10 plus 6/10. That's 1/10. Okay, so we have 1/10 cubic units. All right, 1/10 cubic units, and there's my volume. Okay, that's done by squares, and now what we're going to do is do with equilateral semicircles. Part 2 is with semicircles. And I'm running out of room, so I need some space here. Let me grab some space. Alright, that's what's cool about this. Alright, let's work with semicircles now. Now, semicircles deal with the area. The area of a semicircle is simply going to be 1/2 times pi r squared. It's going to half a circle, right? So what we need is a radius. So let's go back up here. Now this distance right here is your base of the cross section. That will be the side of the square. It will also be the diameter of the semicircle. And remember, what we have to do to get the radius is take the diameter divided by 2 to get the radius. Alright, we know this is 1 minus cube root of y, but I've got to divide it by 2 to get the radius. Okay, so I've got 1/2 times pi times my radius squared. And again, it's 1 minus the cube root of y, alright, divided by 2, because I got to take the diameter and divide that by 2. Okay, so how do we do this? Well, we got to square this guy. And I've got to square the 2. Let me see. If you square the denominator, you get 4 times the 1/2. So 1/4 times 1/2 is 1/8 times pi is pi 8. So I get pi 8 here. And I need to square this binomial. And so I do that. 1 minus, and I multiply double. And I square the last. Okay, and I get y to the 2/3. Okay, now notice that's the same as above here too as well. And so I could use the results from the previous one if I'd like to. When I integrate to get the volume from 0 to 1, I have to integrate pi 8 times 1 minus 2 times y to the 1/3 here. 1/3 plus y to the 2/3. We already did this, so we know a lot about it. This time my constant is pi 8, as compared to before it wasn't pi 8. It was, so really I just take my previous answer 1/10 and multiply it by pi 8. Alright, I'm going to get pi 80th as my final result here. So I'm just going to state it here since it's fairly simple. Pi 80 cubic units. You can verify that in the calculator as well. Alright, now let's do it with equilateral triangles now. Okay, now this time though, up here at the very top, you got equilateral triangles. So what does this look like? Well, let's see here. Let me draw one. No. Okay, there's an equilateral triangle there. Alright, I need to know the formula for the area of an equilateral triangle. And again, my base is at the side. Okay, that's my base. It's going to be 1 minus cube root of y again. So my a of x here for an equilateral, if you guys remember, it's side squared times root 3 divided by 4. So my a of x this time is 1 minus the cube root of y, alright, to the second power times root 3 divided by 4. That's my a of x. So my constant here is root 3/4. I want to integrate this now from 0 to 1. So my volume is the integral from 0 to 1 root 3 divided by 4 times 1 minus y to the 1/3 squared dy. This is going to be root 3 divided by 4 times a tenth again from my previous result from the first one, because I keep on repeating the same integral. And root 3 divided by 4 times 1/10, let's write it down. Alright, times 1/10 for my first result gives me root 3 divided by 40 cubic units here. And the last thing I need to do is rectangles with height 2. So for a rectangle, my base is the 1 minus cube root of y, and the height is simply 2. So height equals 2 here. So my a of x is pretty simple. It's going to be length times width, or in this case, it's going to be 1 minus the cube root of y times 2. So my volume now becomes the integral from 0 to 1 of 2 times 1 minus y to the 1/3 power. Alright, dy. And then this one's fairly simple. Pull out the 2, and you integrate the 1 here, so it's going to be 2 times the integral of 1, which is y, minus MC y to the 1/3 plus 1, which is 4/3, divided by 4/3, which is multiplied by 3/4, evaluated from 0 to 1. And what you get is 2 times 1 minus 3/4 minus 0 here. And then 2 times a 4th, well, that's going to be 1/2. So 1/2 cubic units for my volume here. All right, pretty simple problem if you take it step by step. Okay, last problem. We're going to use the shell method here to find the volume of solid generated by taking this bounded region across the line x equals 5. So let's graph it first and see what happens. Okay, I need to find my intercepts first. So 4x minus x squared equals 0. I'm going to factor out an x here, and I get 4 minus x here equals 0. So x equals 0 and 4. So this parabola, this downward facing parabola, intersects here and at here. This is 4, this is 5. Here's my vertical line. Axis for evolution, x equals 5. My parabola, see 2, that's 8 minus 4 is 4. Okay, so my parabola looks like this here. And y equals 0, this is the x-axis again, guys. So you know it's bounded between the x-axis and the parabola, so my bounded region is in through here. And I need to reflect this across. So when I do that, 4 comma 0 goes over here, right 4 units, up here at 4. So here's my reflection. When you reflect it across the line, x equals 5. And I've got to, let me highlight this here. So when you reflect the yellow across the line of reflection here, you get the blue. And then you got to do the shell methods here. So let me do a cross section here. Show you a typical shell. Okay, there's my shell. My radius is seen here. There's my radius. Here's my height. My height is a y value given by this function here. Thickness is dx here. My radius is found by going right minus left. So here you're at 5, and here, well, let me see. This distance, let's call this distance x. This distance is obviously 5, and my radius is here, r. So r is 5 minus x, right minus left. So radius is equal to 5 minus x. Now let me just say that again. I found that by taking right minus left because it's horizontal. Alright, height is a y value, which is equal to 4x minus x squared. And I want to use a shell method, so my shell volume is going to be circumference, 2 pi r, but my r is 5 minus x, times my height, which is 4x minus x squared, times the thickness dx. My shells are built by taking cross sections vertically, so from 0 all the way to 4. So my total volume is found by taking the integral from 0 to 4 of 2 pi times my radius, 5 minus x, times my height, 4x minus x squared, dx here. And what I want to do is multiply binomials and distribute through. Let's simplify a little bit here. So we'll get 2 pi times the integral from 0 to 4 of 20x minus 5x squared minus 4x squared plus x cubed dx here. Let's continue down here. 2 pi times the integral from 0 to 4 of 20x minus 9x squared here plus x cubed dx. All we have to do is integrate now and evaluate and see what we get. So the integral of 20x would be 10x squared minus 3x cubed plus x to the 4th divided by 4 from 0 to 1. So what do we get here? We get 2 pi times, and you just got to substitute in 4 here. 16 times 10, 160. Minus 3 times 4 cubed. All right, plus 4 cubed. 4 to the 4, excuse me, divided by 4 from That's what you get when you evaluate it, minus 0. Everything evaluated 0 is 0. And so what did we get? We get 2 pi times 160 minus 64 times 3 is 192 plus 4 to the third, which is 64. Combine all this, you get 2 pi times 32, which, believe it or not, becomes 64 pi cubic units. And there you go. All right, there's your example on the shell method there. Give that a shot, and I'll see you later. And remember, this is a video, so if I went too fast, repeat it, take a look at it. Try to do this on your own, and try to do as well as I do. All right, I'll see you tomorrow.